Hello everyone, my name is Sophia Arfin Khan, and today I'm going to talk about the fluorescence spectroscopy and also the microscopic instrumentations of fluorescence microscopy. I'll start from the very basic principles of fluorescence and then I'll go through the instruments used in this technique. These are the major divisions of my presentation, which are the principles, instrumentations, and the applications. Now let's put some lights in this topic. So fluorescence is a kind of photoluminescence. We know that photo means light and luminescence is the emission of light from any substance which occurs from electronically excited states. Now luminescence is further divided into. This is the Yablonsky diagram, which is named after Professor Alexander Yablonsky, who is also known as the father of fluorescence spectroscopy. So this diagram is usually used for explaining the absorption and emission phenomena of a molecule. First, let's see what these notations are denoting here. So S0 is the singlet's ground state and S1 and S2 are the singlet excited states assigned as per their energy levels. Here T1 is the triplet excited state. Now these energy states are further divided into the vibrational energy levels, defined here as 0, 1 and 2. So when light falls upon, absorption takes place and fluorophores get excited from ground level to some excited states. Now generally fluorophores get excited from the lowest vibrational level of the ground state to some higher vibrational levels of the excited states. This transition is very fast process, as I have mentioned here, that it takes around 10 to the power minus 15 seconds. So it's a very fast process actually. After this, the molecules rapidly relaxes to the lowest vibrational level of the excited state, which is also known as the internal conversion and which takes around 10 to the power minus 12 or less time to be occurred. Now then these molecules, after coming to the lowest vibrational energy state of the excited state, this molecule comes or further relaxes to the any higher vibrational level of the ground state. Now this relaxation process can occur either by a non-radiative process as heat or a radiative process like fluorescence. So due to this, as it relaxes to the higher vibrational level of the ground state, the emission spectra is generally mirror image of the absorption spectra, and I'll talk about this later in more detail. This relaxation of molecules from excited state to the ground state can also occur in a different pathway, like here. So what happens is the molecules in S1 state undergoes a spin conversion to the first excited triplet state. Now emission from T1 is known as the phosphorescence, and this conversion which is occurring here is known as the intersystem crossing. This transition from T1 to S0 is a forbidden transition and it takes longer time than the phosphorescence. This transition or relaxation can again occur via non-radiative pathway or via radiative pathway as phosphorescence. So here I have again shown that how this uh, like I've mentioned that singlet state and triplet state, and so what's actually happening. So when this electron is getting excited, it is not, the spin is same, it is not getting changed after excitation, but here we can see that after intersystem crossing the spin is getting changed. So this state is the triplet state, and again when it's relaxing it's again changing its spin uh, like it was before. So this process is known as the phosphorescence and this process is known as fluorescence. So if we look into the frequency trends of these three processes like absorption, fluorescence and phosphorescence, it can be easily understood from the energy difference between the states involved in these processes that the frequency of absorbance is greater than the frequency of fluorescence, and which is greater than the frequency of the phosphorescence, which is easily understood from this energy difference between the states. Like you can see here that the energy difference between this S2 and S0 is greater than this S1 S0, and which is further greater than this T1 S0 energy differences. Now this electronic transitions actually follows Frank-Condon principle, which states that as the transitions are very rapid or very quick, only electronic transitions occur, but internuclear distance does not appreciably changes. So these are the harmonic potentials and these are the vibrational levels in these particular states. And we know that molecules are more likely to reside into the lowest vibrational level of the ground state. So when transition takes place, according to this principle, no internuclear distance changes, so only vertical transition or vertical changes is occur, but no changes in the R value occurred. So we can't draw a line like this, we can't show any transition like this, as due to this transition the R value changes, which validates this principle. So again, if we look from the wave function point of view, we can state from that point of view that the most likely or most favorable transitions are those which shows the maximum overlaps of the wave functions. So I have shown here the wave function of different levels. When excitation occurs, the molecule can go any of the vibrational states of the excited state. So here we can see clearly that this 0,0 transition is the most likely one, as the wave function is overlapped maximum here. So the intensity of this transition will be higher than the other transitions, and as here no vibrational energy changes is occurring, so this is also known as the adiabatic transition. Now here we can see that the R equilibrium of both the ground state and the excited states are almost equal. Now if we shift the potential, then what will happen? So here the R equilibrium of the ground states and the excited states are not equal. So in this case, the most likely transition is like only for this case the most likely transition is from this 0 to 1 transition, as here the overlap is maximum. So we should not get confused with this, because of course we will square it, and after squaring it we can see that this overlap is the maximum one. So this transition will show again the maximum intensity, and the intensity of this transition will be higher than the other transitions. There is another very important phenomena, which is the Stokes shift. So in the Jablonski diagram you have seen that the frequency of absorbance is greater than the frequency of the fluorescence, or we can also say the wavelength of emission is typically less than that of the absorption. Now this shift in wavelength of emission from the wavelength of absorption is known as the Stokes shift. As this phenomenon was first experimented, or this phenomenon was first observed by Sir J.J. Stokes in 1852. So his experimental setup was quite simple. He used the sunlight as the source of excitation, and a stained glass window was used as filter. Now this window selectively transmitted light below 400 nanometer, which absorbed by the sample quinine. The incident light was then prevented from reaching the detector by a yellow glass, which was actually a glass of wine. Now quinine fluorescence occurs at 450 nanometer and was visible to Sir J.J. Stokes. So this yellow glass is actually doing what? Now this is actually blocking the light having wavelength below 400 nanometer and allowing selectively the lights above 400 nanometer. So from this experiment, the shift in the wavelength was easily understood by Sir J.J. Stokes. In the previous slides, I have already mentioned that emission spectra is generally mirror image of the absorption spectra. Now this can be understood from the Cauchy's rule, which tells that the lowest singlet state is generally responsible for the observed fluorescence. And also this state is responsible for the long wavelength absorption band. So what happens is, upon excitation into higher excited states and vibration levels, the excess energy is quickly dissipated and the fluorophore comes to the lowest vibrational level of the excited state. Now this is a very quick process which takes around 10 to the power minus 12 seconds, which results in the same emission spectrum irrespective of the excitation wavelength. Now this symmetric nature of absorption and emission spectra is known as the mirror image rule. The generally symmetrical nature of this spectra is a result of the same transitions being involved in both the absorption and emissions. Like from this uh, from these two images, like we can see, if we notice this green transition, we can easily see that both the absorption and emission transition are similar. So this leads to the symmetric nature of the absorption and the emission spectra, and which is known as the mirror image rule. Now there is some important properties of fluorescence. These are the quantum yield, fluorescence lifetime, and quenching. So quantum yield is the uh, ratio of the number of emitted photons to the number of absorbed photons, or we can also say the ratio of the rate of fluorescence to the rate of all the processes. So we have already seen in the Jablonski diagram that there are many non-radiative processes which occurs along with the radiative process like fluorescence. So what are these non-radiative processes? These can be like the heat, like it can be the internal conversion, and also the intersystem crossing. So this all this non-radiative process occurs side by side this radiative process. And quantum yield is the ratio of this rate of fluorescence to the rate of fluorescence plus the rate of the all the non-radiative processes. Now this quantum yield parameter is independent of the concentration of the system, and it only depends upon the properties of the molecules. When the non-radiative process, the rate of the non-radiative process is smaller than, very much smaller than the rate of the fluorescence, that time quantum yield is tends to unity. When both of this process has similar rate, at that time quantum yield is nearly 0.5, and when the non-radiative process is the rate of non-radiative process is very much higher than the rate of the fluorescence, quantum yield tends to 0. So again we will see in the case of intensity also, when the non-radiative process is very high, that time it actually uh, quenches the intensity of fluorescence, and this is called the quenching actually. And also when uh, there is a high chance of phosphorescence, it again affects the intensity of fluorescence. So again it decreases the intensity of fluorescence, which is called the quenching. I'll discuss about it in my later slides. The next important characteristics of a fluorophore is fluorescence lifetime. So fluorescence lifetime is the average time molecules spend in the excited state before returning to the ground state. Now let's understand this from this simplified Jablonski diagram. So when light is being absorbed, the molecule get excited from this ground state to the lowest vibration level of the excited state, and this and here a population is created after absorption. Now we know that absorption is a very quick process, so this population is created very quickly or instantaneously. Now let's say that the concentration of this state is n star, and of course this population will not uh, stay there for longer. After some time, after very few seconds, of course this population will start to decay, and this decay will happen both through a radiative process and a non-radiative process. So both of this process actually depopulated the excited state. Now if we consider this population is changing as minus dn star dt, so that will be equals to the uh, addition of this rate constant, which is that kf n star plus knr n star. We can also write this as minus dn star by n star is equals to kf plus knr into dt. So by integrating both the sides and applying the boundary conditions, which is what at t0 the maximum concentration is n star 0, and after time t the concentration will be n star t. So we can get this equation, which is n star t is equals to n star 0 plus e to the power minus t by tau, where tau is equals to 1 by kf plus 1 plus knr. So this tau is known as the lifetime of the fluorophore. And if we plot this equation, we will get a exponential decay curve like this. And from this curve, we can see when the t is equals to tau. So if we put in this equation t is equals to tau, so it will become instead t is equals to instead 0 plus e to the power minus 1. So this concentration will be 67% decayed by this time when t is equals to tau. So the major decaying process is happening when tau is greater than t, and only remaining 30%, 37% decay is happening when t is greater than tau. When in this process, when there is no non-radiative decay, that time the lifetime become as 1 by kf only, and this is known as the intrinsic or natural lifetime. And this intrinsic or natural lifetime is related to the lifetime as tau is equals to tau naught phi, where phi is the quantum yield. Now this fluorescence lifetime is not dependent upon the concentration, so it is solely the characteristics of the fluorophore. I have already introduced this concept in my previous slides, that is the quenching. So what is quenching? Now the decrease in the intensity of the fluorophore is known as the quenching, and this quenching can be occurred by various processes. One is the static quenching, where the fluorophore make a complex with the quenchers, and another one is the collisional, where it collides with the quencher. So along with this radiative and non-radiative process, there is another relaxation process which affects the intensity of the fluorophore. So there are some common quenchers like oxygen, halogens, amines, and from these equations, uh, we can also get the rate of the quenching, which actually affects the intensity of the fluorophore. And so this is the reconstructed quantum yield what we uh, get when this quenching phenomena is happening, where phi is equals to kf by kf plus knr plus kq, where kq is the rate of the quenching. And if we compare the quantum yield when there was no quenching with the quantum yield where quenching is happening, and we take the ratio of these two quantum yield, we will get an equation like this, uh, which is known as the Stern-Volmer equation. And from this equation, we can also see that the more the value of kq, more is the quenching. So general trains of halides are these, where iodine is a better quencher than the bromine, uh, than that of the chlorine. Now let's come to the instrumentations. So most spectrophotometers record both the excitation and the emission spectra. Now, what is the emission spectra and the excitation spectra, right? So, what we do is first, when the light is getting absorbed, the molecules get excited, right? And after excitation, it comes back to the ground state. Now, after excitation, it then comes to the any vibrational energy levels of the ground state, which we have already seen in the Jablonski diagram. So it can comes to the any vibration levels of the ground state, and it if we plot the intensity versus the wavelength, we will get a curve like this. This is known as the emission spectra. And what we are doing here, so we are exciting using a fixed wavelength. We are exciting using a constant wavelength, and then after the excitation, uh, the molecules are coming back to the different vibration level of the ground state. And when we are checking the intensity, we are getting this kind of plot, and we can see that at a fixed wavelength we will see a maximum intensity. Now we know that at lambda 3 the intensity is maximum. Now if we want to see that how is this intensity changing when we are changing the excitation wavelength. So in the next, what we will do, we are monitoring this intensity at lambda 3, and here we are changing the excitation wavelength. So previously we took this, we plot this emission spectra where we excited the molecule using a fixed wavelength of excitation light. But here what we are doing, we are monitoring this intensity at lambda 3, this intensity, and we are changing the excitation light wavelength, and then we are observing. So after that we get this kind of plot, uh, and this is known as the excitation plot or excitation spectrum. Now a basic instrumentation of fluorescence spectroscopy contains a light source, excitation filter. Uh, then, okay, so what is this excitation filter is doing? So this excitation filter is actually uh, transmits the light source in a specific wavelength. So only a specific wavelength of light it actually filters out. And after that, this light falls upon this dichroic filter, and this dichroic filter is a special kind of filter. What it does now, it actually transmits the emission light and reflects the this excitation light. I'll talk about it later in more detail. And next is this emission filter, which transmits this emission light only, and through this the light goes to the sample holder where our sample is there, and after it's interacting with the sample, it comes back to the dichroic filter. This dichroic filter transmits the emission light and reflects the excitation light, and after transmitting the emission light, it comes to the emission filter. Now again this emission filter disperses the lights and it detects the wavelength. So here I'll talk about the different components of this instrumentations, which are the light sources, monochromators, filters, and detectors. Now light sources are a very important component, and for different setup of instruments we use different types of light sources, as the different light sources have its own advantages and own limitations. So we can't use uh, one light source for different instrumentation setup. Now here I have listed different kinds of light sources, and nowadays we mostly use this laser or the semiconductor types of light sources, and an ideal light source must yield a constant photon output at all the wavelength. Although in general this is very difficult to get this kind of light sources, but still we can achieve this by using we can mostly achieve this by using laser, as it emits monochromatic radiations, and and we can also get it from a wide range of lasers is available in the market. So these are the types of lasers uh, that we use in general, and I have also mentioned here if these are the continuous or pulsed one. Classic laser sources usually only provides one single narrow emission. Of course, there are some solid state lasers that are tunable, but they are only tunable up to a specific range. But light, white light laser provides a broad range of tunability. So what happens is an source of IR laser emits light pulses, which is used as a seed, and these pulses subsequently amplified and focused on the photonic crystal fiber. Now, this PCF contains some narrow tubes or hollow tubes in the center of the fiber, and a non-linear process happens there at the surface of the tubes, which causes monochromatic light. And this monochromatic light spreads over a broad spectrum. Now, next it is connected to a tunable filter which selects a single light of this broad spectrum, and then it falls upon the sample. So this due to this unique combination of white light laser, it is very much useful as it has a high tunability and it provides a broad range of uh, excitation sources. So this is very much useful and generally the only light source for the one of the most not only but one of the most used light source for the confocal microscope, and I'll discuss about that confocal fluorescence microscope in my later slides. There is another kind of very useful laser which is the semiconductor laser, and so in this laser it uses a PN diode which is connected to a forward bias. Now this is the active region where light generation occurs. It is made up with semiconductors material which has a direct band gap. So when forward bias is applied, electron from the N type and holes from this P type is injected into this active junction or active region, and after coming into this region the electron and holes recombine and it releases some energies in the form of the photons. Now these photons can further stimulate this process, this electron hole pair recombination process, So this process get amplified, and when the light reaches a certain threshold, it escapes through this lens as a coherent beam of light. Monochromators are used to disperse polychromatic or white light into various colors or wavelengths. Now, this dispersion can be achieved using prism or diffraction gratings. The performance of a monochromator is depends upon the dispersion and how efficiently it can block the stray lights. And also the slit width is a very important feature of the monochromator. Uh, like if it has a wider slit, then it increases the signal levels, and therefore also it results higher signal to noise ratios. On the other hand, the smaller slit yield higher resolution, but at the expense of the light intensity. You can also see from this figure that when the slit is 0.5 nanometer, it provides us higher resolution as it provides us more characteristics features, where in the wider slit uh, this plot does not have these characteristics peaks, so the resolution is low. A monochromator for fluorescent should have a low stray light level to avoid the problems due to the scattering light. Now, monochromator can have planar or concave gratings, where planar gratings are produced mechanically and concave gratings are produced by holographic or photoresist methods. These concave gratings can have few reflecting surface, so it lowers the stray light and can be more efficient. It can serve as both a diffraction and also a focusing element, so it is more preferable for the fluorescence microscopy. So basically there are three categories of filters, that are exciter filters, barrier filters, and dichromatic beam splitters. So that are usually uh, combined together to produce a filter cube like this. Now, exciter filters permits only selected wavelengths from the illuminator to pass through on the way towards the specimen. Barrier filters are designed to suppress or block the excitation wavelengths and permit only the selected emission wavelengths to pass towards the eye or other detector, where the dichoric mirrors are specialized filters which are designed to efficiently reflect the excitation wavelengths and pass the emission wavelengths. So from this graph also uh, it is easier for us to understand that this exciter filter, it only allows the exciter wavelength, where this emitter filter blocks this exciter wavelength and only permits the emitter wavelength. On the other hand, this dichoric, what it is doing, it is blocking, it is actually reflecting the exciter wavelength and transmits the emitter wavelength. So these are the working of these filters. Now this dichromatic beam splitter, it from this cube we can see there's this dichromatic beam splitter is actually oriented at a 45-degree angle to the light passing through the excitation filter and at a 45-degree angle to the barrier filter also. So most of the today's excited filters are the interference types. Some barrier filters are also interference type, and dichromatic beam splitters are specialized interference filters. So these filters can further be categorized into different categories based on their work. So there are these short pass filter, long pass filter, and dichromatic beam splitter, which I have already explained. So this short pass filter, what it do is that it actually pass only the short wavelength or shorter wavelength and blocks the longer wavelength. On the other hand, this long pass filter, it blocks the shorter wavelength and passes only the longer wavelength. And already I have explained this dichromatic beam splitter also from this graph, that it reflects the shorter wavelength and transmits the longer wavelength. Now, bandpass filter is a filter with a wavelength cutoff both to the left and the right of its curve. So we can see from here, this is the wide bandpass filter. It cuts some of the shorter wavelength and some of the longer wavelength, and then it allows this range of wavelength to pass through it. Where this is the narrowband pass filter, where it again blocks this left hand side and right hand side and only allows a very small range of wavelengths to pass through it. So filter is actually a very important component of the whole instruments, and a proper selection of filters is one of the most important key to successfully construct a fluorescent microscopy. Now let's come to the detectors. So photomultiplier tubes has been widely used for many years as a detector of the fluorescence microscopy. This is a general diagram of a PMT which contains the photocathode and a series of diodes. So this photocathode is a thin metal film which is inside this window, and this photocathode uh, is held at a high negative voltage, and also this series of diodes are held in high negative voltage, and from this to this diode the voltage actually decreases. So it starts from a high negative voltage and then it ends nearly a zero voltage. Now, when an incoming photon falls upon this photocathode, due to this potential difference, it comes to this first diode and it produces 5 to 20 electrons. So, after uh, this photon colliding with this photocathode, it generates photoelectron, which further uh, comes towards this first diode due to the potential difference, and it produces 5 to 20 electrons. Now then these 5 to 20 electrons, due to this again potential difference, go to this second diode, and this process continues until this anode until a current pulse reaches this anode. So this pulse that is generating in this anode is depends upon the voltage that is applied here. So the higher the voltage, more will be the amplification of this PMT. Now there are three very important time characteristics of PMT, which are the transit time, the rise time, and the transit time spread. So the transit time of a PMT is the time interval between the arrival of the photon at the cathode and the arrival of the amplified pulse at the anode. Now typically it ranges from 20 to 50 nanoseconds. Now the rise time is the time required for the PMT anode signal to rise from 10 to 90% of its final level. The most important timing character is the transit time spread. So the transit time spread is what happens is, like, when this incoming photon reaches this photocathode, it is generating a photoelectron which is further coming towards this first diode. Now this photon can comes like this, and and then it can also comes like this direction also, or this direction also. So based on how the first photoelectron is falling upon this diode, it actually further directs the path of this. So if it falls upon this direction, it will go through this path. But if it falls upon this direction, it will changes the path, right? So it will take a different time to reach at this anode. And so as the photoelectrons does not have any restricted path, so it can actually goes in the different paths. So there is an overall transit time spread occurs in this case, and this is a limitations of photomultiplier tube. But again, this is now overcome. This uh, limitations has been overcome in the MCP PMT. So uh, PMT is actually a very useful detector. Of course, it has some limitations, but it is a very useful, and especially it is useful for low level light detection, as it has a high amplifications. So there is another kind of detector which is nowadays very much used, uh, that is the CCD detectors, or the charge coupled detectors. So CCDs are imaging detectors with remarkable sensitivity and linear dynamic range. This CCDs typically contains a large number of, around 10 to the power 6, or a very large number of pixels, and each pixel acts as an accumulating detector where the charge accumulates in proportional to the light exposure. Now the charge at each pixel point can be read out, and it generate two-dimensional images. So nowadays CCDs is not only used in microscopy, but also various kind of instruments, like we know that it is also used in camera, and it's a very useful and very efficient detector. So nowadays it has a very wide usage. Now the next is another very new and very advanced detector, which is the hybrid detector. So this hybrid detectors actually combines the principle of PMT and the avalanche photodiode to create a highly sensitive detecting system. Now the structure of the hybrid detector is, it contains the photocathode which captures the incoming photons and converts them into photoelectrons. Now after that, it has an electron multiplier which accelerates and multiplies the photoelectrons. Next, it has this avalanche diode which converts the multiplied electrons into a measurable electrical signal with high gain and low noise. So we know about the avalanche photodiode, which is a photodetector which converts the light energy into the electrical energy. Here in hybrid detector, they actually using this avalanche photodiode to further amplifies the signal and to make the detector more sensitive. And actually this avalanche detector actually increases the sensitivity, along with it also, it improves the internal gain mechanism, and it generates a high current. So from this graph we can compare the effectiveness of this new hybrid detector. Here they have compared the photomultiplier tube and this hybrid detectors graph, and we can see from here that how this green line, which denotes the hybrid detector, how the efficient is this hybrid detector to detect this wavelength, this range of wavelengths. Now, fluorescence microscopy is widely used in biological science as well as in the material science. But if we only give our concerns to the intensity based imaging, the emission spectra, which is based on the intensity, then it can lead us to some difficulties, as is depend uh, intensity has a great dependence upon the concentration as well as the excitation wavelength of the excitation wavelength. So it leads us to some difficulties. On the other hand, we know that fluorescence lifetime, which is only the property of the molecules, which is characteristics or particular for each fluorophore. So it is more convenient to use fluorescence lifetime for the imaging. So now it is another microscopy which is known as the fluorescence lifetime imaging microscopy, which is based on this fluorescence lifetime. Again, when two fluorophores have having an overlap emission spectra, it was previously very difficult to distinguish between them. But it can be easily distinguished from their fluorescence lifetime, as it is the molecular property. And in conventional fluoromicroscope, also fluorescence microscope, the emission intensity of a specimen is integrated over time to create an intensity based image of the sample, where in the film the decay is used to construct the image. So here it is very much easier for us to know more about the fluorophore and to know specifically the local environment of the fluorophore. For that, film is a very important uh, technique. Now, the measurement of this film can be taken in two different domains. One is the frequency domain, another is the time domain. And both these domain can be uh, interchanged by Fourier transformation. So they are basically related by Fourier transformation. In my next slide, I'll talk about these two domains in more detail. So in frequency domain measurements, the excitation source is an intensity modulated light source. And because of the time lag between the absorption and emission, the emission is delayed in time relative to the excitation. And this delay is measured by a phase shift, which is denoted by phi omega, where omega is the frequency, which is in the radians per second unit. And as the finite lifetime of the excited state, actually it prevents the emission from precisely following the excitation. So this results in a decrease in peak to peak amplitude of the modulation emission, which is measured relative to the modulated excitation. Now the uh, phase shift of this and the modulation also of the emission depends upon the lifetime as well as the light modulation frequency. So now if we come to these to plot we can understand this better. So here we have used this light frequency which is in 2.5 megahertz. Here it is 25 and here it is 250 megahertz. So we can see that here it is lagging more, or the difference is more than these two, right? So as the light modulation frequency increases, the phase shift of the emission increases and the modulation of the emission decreases, and the phase angle phi and the modulation m on the light modulation frequency is used to recover the intensity decay of the sample. Now, the origin of this phase lagging can be understood by this diagram. Now, if we consider a fluorophore, so this is excited when the intensity is at its maximum, and first the modulation frequency is 2.5 megahertz. Then this cycle is 400 nanoseconds. So like we know that how we can calculate this cycle, like it is just the one by the frequency. So as here we're using the 2.5 megahertz, so this cycle is 400 nanoseconds, where when we are using this 25 megahertz, this cycle become 40 nanoseconds, and in the case of 250 megahertz, this cycle become 4 nanoseconds. And now our fluorophore has a lifetime of 5 nanoseconds. So for this cycle, which have a range of 400 nanoseconds, this 5 nanosecond lifetime is a very less quantity. So it does not actually affect, or it is not that much noticed, because relative, because if we compare this two, then for this 400 nanoseconds, this 5 nanosecond is a very small quantity. Now, when we change our modulation frequency from 2.5 megahertz to 25 megahertz, this cycle becomes 40 nanoseconds. So now it is better than before, as it's still small but not as small as it was before. Now, if we change our modulation from 25 megahertz to 250 megahertz, the cycle becomes 4 nanoseconds. In this case, the uh, this lifetime is 5 nanoseconds, right? So now it is much observable than the before conditions. So this lagging is easily understood if we actually compare this is the phase, and this is, of course, we can see this is the uh, time domain calculation, where we actually show the decay in terms of in this logarithm plot. So this can be understood easily why this lag, or why this difference of amplitudes is occurring, or is observable when we use a higher uh, frequency, higher modulation frequency. Now, for a single exponential decay, uh, these two equations are used to calculate the lifetime measurement. So this is the frequency domain lifetime measurement, and which is, of course, we can easily understand that it is uh, depending due to the lifetime, this difference is occurring. So from this phase lagging and from these two equation, we can measure, or we can calculate the lifetime of the fluorophore. For the time domain measurement, the width of the pulse is made as short as possible. It should be much shorter than the lifetime of the fluorophore. So the time dependent intensity is measured, and the decay time tau is then calculated from the slope of the plot like this, which is log I versus time plot. So, or we can also calculate the lifetime at from the time at which the intensity decreases to 1 by E of the starting intensity. I have already talked about this, like when the we know that when T is equals to tau, the intensity at time T becomes the 1 by E of the starting intensity. So I have already discussed about this. So from that equation also we can measure the lifetime. Now here what we actually do, we actually measure the time between excitation and the photo detection in the detector. So what is the procedure here? So first we give one pulse. So excitation occurs and the machine starts to record the time from the very first time the excitation occurs. Now when we will get one photon, or when the first photon detected in the detector, the machine stops recording the time. So when the excitation stops, so first it starts the time when the excitation uh, starts, and then it stops the time when the excitation stops. So this time the detector is actually measuring this time in between. Now let's assume it took 2 nanosecond or 3 nanosecond to detect this photon. Now we will wait for all the molecules to come into the resting position like it was before the excitation. So after all the molecules comes to the resting position, comes to the ground state again like it was before the excitation, we will give the second pulse, and then again it will excite some molecules, and again the moment the excitation starts, the machine will start to record the time. When it will get one photon at the detector, it will stop the time, and let's assume for this second pulse the time we get is around 5 nanoseconds. So by repeating this method again and again, we will get a histogram like this. Okay, and from this histogram, if we fit this histogram in this equation, after that from this equation we can measure this lifetime tau. So this is the time domain lifetime domain lifetime measurement. For this we usually use this uh, time correlated single photon counting process, and what I have just discussed, this is the TCS-PC process actually, and it is use high repetition rate mode locked like picosecond or femtosecond laser light sources, and high speed. Also the detector should be a very high speed and sensitive detector it needs for this measurement. For thick sample, the image gets blurred as the excitation light illuminates all regions of the sample along the optical path and causes fluorescence not only from the focus plane but also from the uh, regions below and above the focus plane. Now, this can be ignored or by this using this confocal fluorescence microscopy. So, confocal fluorescence microscopy is a technique that provides 3D optical resolution. In microscopy, 3D resolution is generally realized by designing the instrument so that it is primarily sensitive to a specimen's response coming from an in-focus plane, or by subsequently removing the contributions from out of focus plane. Now, this is mm, this is the confocal arrangements, where pinhole 1 placed near or in front of the light source in order to form a point-like sources, which is then focused by this condenser lens to the sample. Another pinhole is placed before the detector, which blocks the out of focus signals uh, coming from this objective lens to reach the detector. Now, this confocal arrangement greatly enhances the optical resolutions of this microscopy. So, in CFM, to obtain a full image, or as I've mentioned, a 3D image, the sample is scanned in the both XY direction, both in this direction, and also along with the depth of this direction, which is the Z direction. Now this is called as Z scan. So this Z scan captures the images from different depths of the sample, and after that it combines those images and produces a 3D image. So it can be easily understood from this diagram that in the Z scan what it's doing is first like it can scan this the above surface of the sample. It can scan through this XY plane. After that it can scan deeper inside the sample also along the Z direction, which is known as the Z scan, and then it will again scan this XY direction. So like this, scanning both in the XY direction along with the Z direction, it it creates a 3D image of the sample. So confocal fluorescence microscope shows a high optical resolution, and it scans a very small region of the sample. It actually the scanning process is a point by point scanning. So it focuses on a very small region of the sample, and it only gets the information from that focus region of the sample, and after combining all these points together, it creates a high informative 3D image of the sample. In the conventional confocal, the optical slicing ability is achieved by a pinhole that works as a special filter by blocking the fluorescent light that comes out of the focus that I have already talked about. However, the specimen is illuminated not only in the region of the focus but also in the entire double cone region extending above and below the focus. These shortcomings are overcome in the two-photon microscopy. So two-photon excitation is a fluorescence process that I have shown here. So this is the one photon excitation and this is the two photon excitation. And in this process, fluorophore is excited by simultaneous absorption of two less energetic photons. This nonlinear process can occur if the sum of the energy of the two photons is greater than the energy gap between the molecule's ground and excited states. Since this process depends upon the simultaneous absorption of the two photons, the probability of two photon absorption is a quadratic function of the excitation radiation. Now, this is a basic diagram or general diagram of a two-photon fluorescence microscopy. The two-photon microscopy is intrinsically capable of optical slicing, and no pinhole-based spatial filter is needed here to block the signal from the out of focus region. Again, As the probing light is of longer wavelength, so less scatter occurs than the shorter wavelength light, and it allows one to explore the samples at a deeper penetration depth. And also, as it has a longer wavelength, they have higher Stokes shift, and due to this, it is easy to separate in comparison to the any regular fluorescence microscopy. So fluorescence microscopy is an efficient tool for visualization of biological molecules and to understand the material's property at molecular levels. Now here I have mentioned some of the applications of the fluorescence microscopy. Uh, with advancement of this technique with time, researchers from various fields are also interested to use this technique more frequently, as this is capable to provide us the insight of the molecular interactions. So, in this talk, I have discussed about the basic principles of the fluorescence resulting from the electronic transition, the principles and the rules involved in this uh, fluorescence technique, like the Frank-Condon principles, Kasha's rule, and then I have talked about the instrumental components of fluorescence spectroscopy along with the new advanced techniques of this fluorescence microscopy and their workings also. I hope this talk was useful and I was able to explain things properly. Thank you.